Welcome to the first pre-recording of the Programming Languages virtual meetup. My name is Connor Hoekstra, and in this video we're going to be covering Chapter 1.1 of the free textbook, The Structure and Interpretation of Computer Programs. Right off the top, though, I want to talk about what the goal of the Programming Languages virtual meetup is. In this meetup, we're going to be working through books together on programming languages. And ultimately, the goal is to grow our knowledge on programming languages and programming language principles, design, and implementation. And if we do this correctly, this will ultimately lead us to the ability to write code that is more readable and expressive, maintainable and scalable, and beautiful and idiomatic, all things that I care very deeply about. And learning with a group of people is always more fun than learning on your own, which is why I set this meetup up. The format of the Programming Languages virtual meetup, at least to begin with, is going to be meeting for 1 hour once a week. That's Mondays at 8 p.m. Eastern Time. For the first 10 to 15 minutes, I'll be giving a presentation sort of on the summary of what we covered and also just random things that I found while Googling. And for the remaining 50 to 45 minutes, there'll be just discussion. So everyone's going to have different insights. They're going to find different parts of the material more interesting. And it's just going to be a discussion to talk about what we learned and what we thought was cool. And each of these presentations I will pre-record. So if you're not able to attend the meetup, you can still sort of follow along just if you're subscribed to my YouTube channel, because I realize that 8 p.m. Eastern Time is going to be not convenient for people in certain parts of the world. So why are we starting with SiC PD, the Structure and Interpretation of Computer Programs? So this book has been on my to-read list for a very long time. If I remember correctly, the first time I heard of this book was when I was listening to my favorite podcast, Functional Geekery, on episode 1. The guest was Uncle Bob, who's a well-known individual in the programming community. And the first 10 minutes of the episode, the host and Uncle Bob talk about this book. And at one point, Uncle Bob says, "It is pretty amazing. It was startling for me to read it. It has become a kind of Bible for me." And when someone that prolific in the software development and programming community makes a statement like that, obviously it puts that book on your list. The second time, or at least the second notable time that this book came up, was during a Bay Piggies user group meeting, which is the Python meetup in the San Francisco or Bay Area. When I lived down in California, there was a presentation in which the presenter had a slide with 5 books every programmer should read. And if you note, the second from the right is SiC PD. And notably, the speaker also mentioned that concepts, techniques, and models for computer programming, he considered at least the unofficial sequel for the structure and interpretation of computer programs. So this book, the CT MCP, is definitely going to be covered in one of the follow-up books once we complete SiC PD. So for these sort of 2 reasons, this is why we're covering it. A lot of people have said really great things about it, and it's been used as a textbook at MIT for many, many years. So should be great. Other books that we're gonna go through after we finish SiC PD, in no particular order. These are just books that I would like to cover at some point. As I mentioned, Concepts, Techniques, and Models for Computer Programming, Mastering Dialog APL. APL is one of my favorite languages. Beautiful Racket. Racket is becoming one of my favorite languages. Types and Programming Languages. I've heard this book is a little bit more difficult, but I think after going through SiC PD and Concepts and Techniques, it should be doable. Also, 7 Languages in 7 Weeks by Bruce Tate, I've heard amazing things about. There's a sequel to this one, 7 More Languages in 7 Weeks, and I've heard that Bruce is also working on another follow-up to this one, so a third in this series. And there's also the option of doing language-specific books so that aren't sort of generic. I know we have APL and Racket. Understanding Computation is another book on my list, and specific to C++, which is where my expertise is in, functional programming in C++, and design patterns in modern C++. Note, though, that at the end or close to the end of this book, Structure and Interpretation of Computer Programs, I'll poll those that are going to be joining for sort of the next book, and we can vote on which book people are interested in. So, as I mentioned before, this video is going to be covering Chapter 1.1, so without further ado, let's jump into it. So, this is the table of contents for Chapter 1.1 and the dedication forward and preface to the second and first editions, which I also read through as well. And for the first bit, I'm just going to highlight the certain quotes that I thought were interesting or fun, and I'll sort of expound on different digressions that I took when I was on Google. And at the end, we'll also briefly cover some quotes and highlights from the corresponding lecture to this chapter. All the links for the video lectures, the free textbook, and any of the things that I mentioned in this video will be in the description down below. So the first quote comes from the dedication of this chapter, and it's from Alan J. Perlis, who said, "I think that it's extraordinarily important that we in computer science keep fun in computing." And I think this is a great quote to start off the sort of summary of this chapter and this book. And it's really awesome to see someone so prolific. Alan J. Perlis is a very, very prolific individual in sort of the history of programming languages, talking about how we should try and keep programming fun. So who exactly is Alan J. Perlis? He is the first recipient of the Turing Award, basically the Nobel Prize of Computer Science. He was also on the ALGOL committee, which is basically a team that was responsible for developing ALGOL, which was basically one of the most influential programming languages ever. If you're programming in a programming language today, odds are ALGOL influenced it in one way or another. He was also the first president of the Association of Computing Machinery. He was a professor at several different universities, Purdue, Carnegie Mellon, and Yale. He wrote the Epigrams on Programming, which is a famous list of quotes by him. I think there's like 100 plus or 110 or so. A couple of them that you may have heard of. A Lisp programmer knows the value of everything but the cost of nothing, and it's better to have 100 functions operate on one data structure than 10 functions operate on 10 data structures. And on top of this, he is the author of one of my favorite papers in praise of APL, A Language for Lyrical Programming. I'm not going to talk any more about that because probably in one of the future books that we cover, we'll be talking about or covering an APL book. So anyways, Alan J. Perlis, prolific individual, first recipient of Turing Award, first president of the ACM, helped develop ALGOL, definitely someone you should know about. The next quote from the foreword, also by Alan J. Perlis: "A programmer should acquire good algorithms and idioms." So it turns out before Sean Parent from the C++ community said that you should know your algorithms, Alan J. Perlis was saying it decades before. So if you're not familiar, Sean Parent is a senior scientist or distinguished scientist at Adobe, and he's worked on Photoshop for many years. And he gave a prolific talk in 2013 called C++ Seasoning, where he said the following: so you have all these algorithms at your disposal, learn them, that's very important. I've basically quoted this in every talk that I've given at every conference because I believe so strongly in knowing your algorithms. When you have a rich standard library, you should learn to rely on that instead of hand-rolling your own for loops and writing your own algorithms whenever you feel like it. The next quote that I have is: "The discretionary exportable functionality entrusted to the individual Lisp programmers is more than an order of magnitude greater than that to be found within Pascal enterprises." So Pascal is another programming language that was, I believe, invented by Nicholas Wirth, who is once again another prolific individual in the history of programming languages. And this quote by Perlis is basically saying that the power that Lisp programmers get is an order of magnitude, so 10 times greater than individuals that are programming in Pascal. So I find this quote interesting because something similar was said about APL. It might have been Perlis that said that as well. And it's sort of not a well-known fact, but there's a certain number of individuals that think if you have to learn sort of a more, I won't say esoteric, but today compared to Python, Java, C++, sort of mainstream languages like that, to learn another language that is a little bit different than that, you should be getting a huge sort of win, whether that's like an order of magnitude in terms of power or in terms of productivity or in terms of performance. There should be a reason to switch from whatever mainstream language you're using, and Perlis is arguing that you get that in Lisp compared to Pascal at least. The next quote is a very long quote. It's split across 3 slides. Lisp changes. The scheme dialect used in this text has evolved from the original Lisp and differs from the latter in several important ways, including static scoping for variable binding and permitting functions to yield functions as values. In its semantic structure, scheme is as closely akin to Algol 60 as it is to early Lisps. Algol 60, never to be an active language again, lives on in the genes of Scheme and Pascal. It would be difficult to find 2 languages that are the communicating coin of 2 more different cultures than those gathered around these 2 languages. Pascal is for building pyramids, imposing, breathtaking, static structures built by armies pushing heavy blocks into place. Lisp is for building organisms, imposing, breathtaking, dynamic structures built by squads fitting fluctuating myriads of simpler organisms into place. So you can see why Perlis is, his paper on APL is one of my favorites. He has a way with words, and this is just beautiful. So it points out that not only is Scheme a descendant of Lisp, but you can consider it a descendant of Algol as well. And he sort of compares both Pascal and Lisp to each other in terms of these metaphors of building pyramids and organisms, which I think is just beautiful. Another Lisp quote, so Scheme, the dialect of Lisp that we use, is an attempt to bring together the power and elegance of Lisp and Algol. So once again, it's being highlighted that Scheme is a descendant of Lisp and Algol. And a third Lisp quote is that to reiterate, the dialect of Lisp used in this book is called Scheme. And so at this point, I wanted to go figure out what is the actual relationship between Scheme and Racket, because I had heard on many podcasts that Racket is a descendant of Scheme, but that also the group that created Racket, the PLT research group, had created something called PLT Scheme. And so I went and did a bunch of research on sort of the history of Lisps. And the most useful thing that I found was this timetable on Wikipedia of Lisps, and you can see how many different dialects of Lisp there are. So in the late 50s, Lisp was invented by John McCarthy. And then for the next, 5-6 decades, many more Lisps or dialects of Lisps were invented. So these are the ones that I could find that had logos. Scheme in the mid-70s was invented. Common Lisp was standardized in the early 80s. Emacs Lisp is a very popular dialect of Lisp used with the Emacs IDE or editor. Pico Lisp is another Lisp. PLT Scheme is a descendant of Scheme. Like I mentioned before, this was created by the PLT research group, and you can see that in the 2000s, it was later renamed to Racket. So that's the relationship between PLT Scheme and Racket. It's just a renaming, so they're basically the same thing. Guile is a version of Scheme implemented by GNU, and Clojure is one of the more recent and popular dialects of Lisp. And also Hi, I'd never heard of it, but when I was doing my research, I found that it's basically a Python flavored Lisp. So it's a Lisp wrapper around the Python interpreter, which is neat. So the 2 most popular, I think, today dialects of Lisp are Racket, which is used a lot for educational purposes, but it's also a full-blown programming language that is used in production at many companies, and Clojure as well. This was invented by Rich Hickey, who's very well known in the Lisp community, and I think in the programming languages community at large. So to highlight once again, Lisp invented in the 1950s. It went on to inspire Scheme, which is a dialect of Lisp, and then Scheme went on to inspire PLT Scheme, which was later named to Racket. So and it's important to note that it wasn't just Lisp that influenced Scheme, it was Algol as well. So 1950s, McCarthy invented Lisp. The Algol committee invented Algol, which included Perlis. The mid-70s, Scheme, this was invented by Sussman and Steele. Sussman, one of the authors of this book, and Guy Steele, is another prolific individual in the programming language community. And then in the 90s, Racket, which was originally called PLT Scheme, was created by the PLT research group. And I think the last thing I'm going to note sort of on this digression of my research into Lisps is when I was looking for what the difference between Racket and Scheme was, I found this Quora post, and at the bottom it links to the Racket Manifesto. I clicked on that link, and that brought me to this page that has the Racket Manifesto. And it's an interesting read, but what I wanted to highlight here is this, the Summit on Advances in Programming Languages. So I thought I was aware of most of the conferences that focus on programming language research, those being POPL, HOPL, PLDI, and now SNAPL. So POPL stands for the Principles of Programming Languages. That happens once a year, typically, I believe, at the beginning of the year. HOPL is the History of Programming Languages. This is a really interesting conference that only happens like once every 13 to 17 years. So they've only ever had 3. And the 4th one was slotted to take place coinciding with PLDI 2020, which was going to take place in June. HOPL has been delayed for the moment, and PLDI, the Programming Language Design and Implementation Conference, has gone virtual. So it's still happening, I believe, the 1st or 2nd week of June, and all of the talks are going to be streamed live, I believe, which is awesome. I wanted to travel to the UK to attend both HOPL and PLDI, but as HOPL is delayed and PLDI is now virtual, we can all just sort of watch from our computers, which is great. And the point here that I'm highlighting is that I guess there is a 4th conference/summit, which is the Summit on Advances in Programming Languages. I was not aware of this one, so it's great to add this to my list of conferences that I can pay attention to. And also, interestingly, on the committee of the HOPL 4 conference that was slotted to happen in June of this year, but is going to happen at some point a little bit later, one of the co-chairs of the organizing committee is Guy Steele, who is, as I just mentioned, one of the co-creators of Scheme. So very interesting. Back to our quotes. We're back to the preface to the first edition. From Lisp, we take the metalinguistic power that derives from the simple syntax, the uniform representation of programs as data objects, and the garbage collected heap allocated data. From ALGOL, we take lexical scoping and block structure, which are gifts from the pioneers of programming language design who were on the ALGOL committee. So this is just a great quote highlighting what was taken from Lisp and ALGOL in creating Scheme. The next quote, at this point, we're getting actually into the content of Chapter 1. Lisp is an acronym which comes from the LIS from list and the P from processing. So if you didn't know that, that's a neat fact. The thing to be multiplied is given a local name X, which plays the same role that a pronoun plays in natural language. I highlighted this quote because it's interesting that they choose to highlight the similarity to pronouns in natural language when in APL, which I've mentioned a couple times before, one of my favorite languages, it stands for a programming language, they actually call their variables pronouns. And they call their functions verbs. And so they sort of mirror the terminology for natural language that here is being contrasted with. In APL, we actually use that terminology, which I thought was neat that they were highlighting that here. The next quote, the formal parameters are replaced by the actual arguments to which the procedure is applied. I highlighted this quote because I hear a lot of times people use parameters and arguments interchangeably, and they are two distinct different things. A function is defined with parameters and it's passed arguments. So a lot of people are probably still going to use these interchangeably, but I think when we can be explicitly precise, it's better to, because it enables clear communication. And this is now sort of highlighting the code examples from the different subsections of Chapter 1.1. Basically, it was just sort of explaining how Lisp works. Here is an example of 5 different expressions. If you want to add 2 numbers together or multiply or subtract, performing any kind of operation, you use prefix notation, which means the operator comes first and then the operands come afterwards. So we have 137 plus 349, but in Lisp, you compute this by going parentheses plus, which is the operator, our 2 operands, 137, 349, and then end parentheses. And you can see this is the same for division, subtraction, and multiplication. And here's another example from subsection 1 of Chapter 1.1, which shows that you can nest these, but it becomes a little bit hard to read, so they recommend, and the format that they use in this book is something called pretty printing, where you vertically align the operands of a certain expression. So you can see here, we're adding on the innermost sort of nesting of these parentheses, these two sub-expressions times 2, 4 and plus 3, 5, and we've aligned the left parentheses here. So whenever you can do that, it leads to more readable code. The next subsection, naming an environment, it just shows here that you can define variables by using the define keyword, and you can also define functions. So at the top, we're defining pi and radius, and then we can use those in our expressions to compute values. And then we can also use define the keyword to define our variable here, circumference, which is basically a composition of our previously defined variables. The next subsection, evaluating combinations. The only thing that I highlight from this subsection of the chapter is they're showing visually a representation of sort of these nested expressions. And this is a good way to think of it. I think the innermost expressions are basically, or the values are the nodes of our tree, and then you have to evaluate the sub nodes in order to get your ultimate value at the top. The next subsection, compound procedures. This is basically just highlighting that you can define functions in terms of other functions. So here at the top, we've defined our square. The notation here, we use parentheses. The first thing our parentheses is the name of our function, and everything else is going to be the parameters. And then the second set of inner parentheses define what our function is actually, the computation it's actually doing. So here we're multiplying x by itself. And then on the next two lines, it defines another function that takes 2 parameters, whereas square only took a single parameter. And we're defining this function in terms of the previously defined square function. So pretty straightforward. You might not like all the parentheses, but it shouldn't be too hard to follow if you're familiar with other programming languages. And then in order to invoke this function, we just pass it the number of parameters that the function requires. So sum of squares 3, 4 is first going to square each of those to get 9 and 16, and then add them together in order to get 25. So the next subsection, entitled the Substitution Model for Procedure Application, just walks us through a simple example of how we substitute variables for expressions, or the definitions of functions for the function names. So here we have f defined to be 5, which we are going to substitute in for the a's. So we initially start with sum of squares, paren, plus a1, n paren times a2. And then once we do our first substitution, we end up with plus 5, 1 and times 5, 2 instead of plus a1 and times a2. We then evaluate the plus 5, 1 and times 5, 2 to 6 and 10 and substitute the definition of sum of squares in for the function name sum of squares to end up with plus square 6, square 10. We then once again substitute the definition of square in for the function name square to end up with times 6, 6 times 10, 10. Which ultimately gives us plus 36, 100, which then gives us the final result of 136. So this is, I think, pretty straightforward, but towards the end of this subsection, they highlight that there is 2 different ways to perform this substitution. The one that was highlighted at first is applicative order, but then they contrast this with something called normal order, where you don't eagerly evaluate your operators and operands. So when we have plus 5, 1, we in the applicative order model, we immediately evaluate this to be 6. But they say that there's an alternative method called the normal order, where we leave this as it is until we ultimately need it. And that would mean that we would end up with, instead of a 6 here, a paren plus 5, 1. And then instead of 2 6s down here, we'd have times plus 5, 1, plus 5, 1. And then at that point, we would evaluate. So it's sort of a way of lazily evaluating our operators and operands, which they mention is not typically preferred because it ends up with redundant and duplicated computations. But they highlight it because they say later in the book they're going to, contrast the two and use one of them to implement sort of a different language feature. The next and last subsection that we're covering, subsections 1.1.7 and 8, just sort of walk through different examples that I'll leave to each of the readers. But in subsection 6, we have 2 different sort of conditional expressions. The first one is cond, which is analogous to what most languages have as a case statement. you basically use cond and then can have as many number of clauses that you want. A clause is made up of a predicate and an action. The predicate is just basically an expression that yields a true or false, and then the action is what will be performed if the clause returns true. So the first one is x greater than 0. If so, we just end up with x because we're defining an absolute function. And the last one is x less than 0. If so, we have to negate x. And an alternative way to define a conditional expression is just using the if keyword. This is for if you only need 2 clauses, in which case you can just basically define one of them and then have an if and an implicit else for the second clause that you don't mention. And I think the next thing that I'm going to show is one of the exercises from section 1.1. And this is to define a procedure that takes 3 numbers as arguments and returns the sum of the squares of the 2 larger numbers. So obviously, after having followed the conditional expression subsection, they want you to use those. But instead of doing that, I'm going to highlight one of my favorite features of Racket, which is probably the language I'm going to use the most. Even though the book uses Scheme, Racket's a descendant of Scheme, so I'm sure most of the examples will work. And the solution that I'm showing here is using something called threading. So threading basically gives you the ability to pipe different algorithms together without having to nest them inside, like recursively inside the parentheses. So without threading, you would have a sort on your innermost parentheses, and then take, and then map, and then fold. Here you can just list them out one by one. So first we're sorting them using the largest numbers first and the smallest numbers last. Then we take the first 2 of these. Then we have a map with a lambda that uses this definition to square the number. Note that in Racket, you can actually use the lambda symbol. If you're using Dr. Racket, you can just, I believe, hit control and then slash, and that'll give you the lambda. And then the last operation is we're summing up those numbers, which we use by which we do by using the fold reduction algorithm. And after this is done, I believe I have a couple things to say just about the corresponding lecture to this. So link, as I mentioned before, down in the description down below for lecture 1 that corresponds to what we covered from the Structure and Interpretation of Computer Programs textbook. The first thing is just some of the quotes that are said towards the beginning of the lecture. And here they are. Magical language called Lisp is the language that we use for this textbook. You can become a master programmer if you really learn the ins and outs of Lisp. The constraints imposed in building large software systems are the limitations of our own minds. I think that's a pretty cool quote to inspire your students. And you want to suppress detail. And I think this goes hands in hand with both what Perlis said about learning your idioms and your algorithms, and what Sean Parent said about knowing your algorithms, is that the professor is highlighting that you use abstraction to suppress detail. And that can be said for so many things in software engineering and programming. When you use an algorithm instead of writing your own for loop, you are suppressing detail, unnecessary detail of the index and how you're incrementing and how you're modifying. If you can just use an algorithm and pass it a higher order function, or just straight up use an algorithm called reverse or rotate, you are able to suppress detail, which makes it easier for the reader. And so the professor mentions this multiple times throughout the lecture, and I thought it was worth highlighting. And the last thing I'm going to show is this very blurry screenshot, which is sort of the summary of the lecture. He talks about how we have shown procedures and data and privative elements, means of combination, and means of abstraction, which are sort of what the professor says are the 3 main things that you should care about when learning a programming language. The primitive elements are the operators and the data. The means of combination are the parentheses for composition, and also the 2 different conditional expressions, cond and if. And then the means of abstraction that we have are the define, which enables us to define methods which then suppress the detail, which is the goal at the end of the day. So hopefully you enjoyed this. If you are watching this in the first 24 hours before when this has been released, we'll be meeting tomorrow night, which is Monday, May 11th at 8 p.m. Feel free to tune in if you want. And if not, the links are in the description down below for all the future meetings and the PLVM meetup page. So be sure to check those out. Textbook, lecture videos, links are also in the description down below. Hope you enjoyed this and have a good day.